So, welcome. Welcome to session 3 of the IoT Kitchen. I'm glad that you came back after 1 month. The last time we looked over antenna tuning and matching. We didn't really have the time to go through the matching part though, but I hope we can cover a bit of that today. Yeah. So what do we do again? Already like the last time, I'm playing around with these antenna kits. So there is this study I want to highlight again. This study, do-it-yourself low-cost PCB antenna design for wireless IoT, was written by Harald Naumann, and yeah, it was financed or sponsored by Neocortec. Neocortec is an interesting wireless mesh technology, and yeah, it is either on LoRaWi on 2.4 gigahertz, so available in 2 variants. And in this study, they discuss different antennas, PCB antennas, different topics about antennas, and you can download this study for free. And in this study, they have different designs of these IFA antennas, and I turned them into real PCBs that you can see here in the pictures. Yeah, it's a great read. Go and download it. You can learn a lot about PCB antennas and yeah, how to what affects it, the performance of these antennas. They discuss their different things like PCB size, for example, batteries that are close to it, and so on. These are only simulations that are covered there, and I think it's a great tool, these antennas, to actually learn a bit how to work with PCB antennas, like how to design them, how to measure them, tune them or match them, or whatever you need to do. It's a great yeah, resource. So this antenna kit, so today I have always 2 cameras in the screen. So if I accidentally miss one, you see a lot of PCBs on the table. These are all basically the same antenna I experimented with. But we have yeah, this SIFA antenna, for example, which is this one. We have a meandered antenna, IFA, so it's another way to do that. We have a dual band IFA, which basically has 2 resonance frequencies, and a normal band IFA. So there are different ways how to get IFA on there, and we also have an L-antenna, which you see already here. I hope I can make this. I can actually make this bigger, I guess. Yeah, here you see it close up, the L antenna, and here the other antennas as well. So you can actually get more information about this kit. You can also buy it from our website. If you buy the kit, you get you get these 5 PCBs. They all have a calibration kit. They have solder masks that can help you, for example, to extend the boards of copper foil to see what happens when you have a bigger PCB. You can also cut them in half if you like to see what happens if you have a very small PCB. They all contain a matching circuit. I updated the design a bit and yeah, also worked a bit on the matching circuit because a 5-port matching circuit can also be a little bit too much. Yeah, you get the layout data and they're available in KiCad and Altium, and you can of course use them in your own designs. And we are currently also setting up production with Elecrow, so you can then purchase them also at Elecrow, and they handle all the delivery. So more on that maybe in the future. So now yeah, all boards are documented. So we set up a wiki for that, where you can see all kinds of things, matching circuits, matching calculations, and board layout. It's all there basically. Measurement data, so you can use that to compare with your own results. And yeah, now to the interesting part, matching and tuning. So we talked about this in the last session. Tuning and matching are two different concepts, but I will make this small recap so that we get everybody up to speed. So tuning basically describes or is a method to change the resonance frequency. So in the last session and the session before, actually, we saw what happens when you take an antenna like this and you put it into an enclosure, right? Then, of course, the dielectric in the near field of the antenna, so the plastic, this will change the effective epsilon r and will shift the frequency down. It will make the antenna look like it's electrically longer, and this is why you have a lower resonance frequency. So it would move the maybe green part or whatever, it would move it down, right? And tuning, if you tune an antenna, you try to move the resonance frequency. And we did this the last time. I think I have a picture about that. I can go more into detail, where we scraped off some parts of the radiator of this SIFA antenna. So if you haven't seen that, you can check out the latest or the last video from session 2. It's also available on YouTube, by the way. You can go and check this out. And yeah, I hope you learn something. I have to from time to time. Yeah, good. Matching. What is matching? So matching is basically, yeah, you could say you make the dip deeper. So when you have an antenna, the antenna does not always have 50 ohms, right? So our ports that we use for RF, they're usually 50 ohm ports, 50 ohm transmission lines, and your antenna might not have 50 ohms at the resonance frequency, but something slightly different. And when you have two, resistance, different or impedances, what you will get is you will get reflections. So a part of the wave is then reflected back, and this is why the dip goes not as deep as you would like to have it in the return loss diagram. So you can also see this in a standing wave ratio, right? The standing wave ratio gets bigger. So if it's 1, you have a perfect match. If it gets bigger, you have a standing wave there. And this means that some energy is not transmitted through the antenna. It's actually coming back. And this is what matching makes. And Last time, right, we looked at this tuning. So tuning was, we take the radiator here and cut it shorter, and we made several measurements basically, and we saw how the frequency moves upwards. So this SIFA antenna, this is a really good match basically. Yeah, it has at the desired frequency, it's just matching very well. It's close to 50 ohm impedance, and so you have a low loss in this case, right? So, but for the matching, you might know this Smith chart. The Smith chart, I don't know, some describe it as the most, yeah, some PDFs, they write above it like black magic chart, but it's absolutely not black magic, and I will not go into detail about like all the theory that is behind that. But basically, what you have is you have somewhere it's just a representation, a graphical representation of your impedance of a complex number, if you like, and yeah, you have, so here is basically 50 ohms is in the middle, so this is pure resistive. You can then go inductive or capacitive basically, and when you make a measurement, basically you get these nice charts. We can actually take a look at that directly. If I think I have to do it like this, huh? Okay, it's not perfect, but so the Smith chart, as you can see here, so this is my antenna, which is connected to the VNA. It's a one-port measurement, so the VNA outputs some power, sweeps over a frequency range, and just measures what comes back. And you then can calculate this Smith chart. So this line is basically drawn from different measurement points that the VNA is producing. And I don't know if you can see this red small circle on this blue line, but this is basically indicating the frequency. So I can move this bar down here. And so this would be 600 megahertz. I would be down here. And if I move up to our desired 868 megahertz, it's round about here, right? Our port is here. So this is where the impedance is at 868 megahertz. So this is not 50 ohms. So this is somewhere else. Yeah, you can actually read the value here. So it says it's 22 ohms plus J 5.9. So it's inductive. It's up here in this region. So the Smith chart is very helpful in this sense to basically do matching, and how it basically works is that you, does this work? Yeah. That you move this point along this chart on certain lines, and you can do this by adding yeah, parallel or serial components. And if you add inductors, basically you move up in this way, and if you add parallel inductance, you move up in this way, and the opposite is true for capacitors basically. So adding a series C will make it more capacitive. You move the thing down here on this curve. And I also won't go into details on the exact Smith chart. This has to be covered in a in one of our in our IoT Academy, where we have more time for that to actually understand a little bit more, which is quite useful. But you can just imagine you have any point. Basically, you want to go to 50 ohms. yeah, then you can just move along with these circles. Yeah, you can move down here, and then you can maybe move up like this. Yeah. And this is what matching is basically doing, and you can see this very graphical in this Smith chart. So we have an antenna. This is a desk view. Okay. We have an antenna connected to our VNA, and you see this is the complete screen. Just you see and this is the curve, and I can basically export this data, this measurement data, to a folder, and then yeah, I already did that, but I will do it again. And then we can switch to some software. So what you can do is use, I like the software Attune. It is, yeah, there's a free and a professional version. I'm just using the free version. It's enough at the moment. And you can basically load the S1P data. And so you see also this graph. You can see here the Smith chart, and here are two markers, 1 and 2. And these markers are located round about here. And you would like to move this point to 50 ohm, because there we have then VWSR of 1. So if you look at the VWSR, you will see that it will not go to 1. It's above 2, right? And this is because it is outside of this circle that you hopefully can see well. So what does Attune give you? So you can use Attune actually also to play around with matching circuits. So let me clear that for the moment. Clear circuit. So what you can do, it has basically a feature that you can say, okay, I have whatever 0603 or 0402 generic multi-layer inductors or capacitors in my matching circuit. I can also work with ideal inductors and capacitors. So the difference is that yeah, inductors or capacitors, like, or even resistors that we have on the board, they are not ideal. They have some inductance and they have some capacitance, and yeah, you can take this into account when you select this. Then they have a model behind it. It's kind of a generic model that yeah, is not an ideal, in this case, I don't know, capacitor, but it is behaving like a capacitor with a little bit of inductance and so on. This is very helpful. There are also components on the market that give you exactly this model data. So RF capacitors that are a little bit more expensive, you often get like a model, like a characterization of this component that you can then use in software to calculate the matching. But this is also out of scope. So what we can do is we can, for example, just play around a bit. We can, for example, say find. So we could start with a circuit, right? So here you have a small circuit. I can try to make that a little bit bigger. So here you have the antenna. Attune thinks the thing that you measure on your VNA is directly measured at the antenna, and there is no lossy transmission line. It's like a perfect transmission line. Everything is perfect, and then you have here your port. So you have your measurement data. Everything is perfect, and then you add in between these matching components to make it work, right? And then you can basically, for example, you can say, okay, I just take a pi circuit and click on matching, auto matching, and then it will calculate and run a small simulation to find basically suitable values for your matching circuit. So, and you can see in the Smith chart that this curve moved down here, right? So this point moved, so the whole thing was basically shifted, changed a bit, so that you have a good match. It's not a perfect match, but it is good. So this brown curve is the simulation, red curve is the measurement, and you can then look at the Smith chart on the return loss chart, and you can see you have this dip and this curve here that you see, this dashed line. This shows you basically the losses that you will have in your matching circuit. There is nothing for free, basically. Yeah, a good match does not necessarily mean that your antenna radiates more, right? Because in the network you will lose some of the power that you wanted to bring to the antenna. So this might not even be the best choice, right? I could go and say, okay, what is with a T circuit, right? Let's do some auto matching. Aha. So it changes a bit, right? Losses get a little bit less, component value changed a bit. And yeah, if we look on the Smith chart, right, we have a perfect match. That's why the line goes basically far down. I kept the scale at -25, so this is why it looks like this. But you have a very nice looking match, but you also have some losses. So you not just want to look at things. So it happens that I don't have all these components here. So what I can also do is I can say, okay, find me the best circuit with, for example, 2 components, right? Would look like this. Find me the best circuit with 3 components. Then we end up at this circuit. But for the sake of this event, basically, this experiment, I would just choose 1 component. Yeah. And what this is basically, yeah, like a filter. This is like a little bit what the filter looks like. And you can see that it's not perfect, right? At the resonance frequency, we move it just a little bit down. We have a match at a higher frequency. And why does it say 1.5 picofarad? Okay, I don't have that. So what I have here, what I found in our lab was a 1.8 picofarad cap. Yeah, and the nice thing is you can actually go here and play around with these values, yeah, and see what happens. Maybe it makes more sense if you go with 2 components, right? And then you can also see, okay, how, if I change this a bit, right? What happens to the matching, right? So it's relatively, I don't know, there's not such a big difference. So this, you can also evaluate your matching circuit with this regards, right? So yeah, this is interesting. So you can play around with that, and you can actually see the series capacitance. What does it do? It moves this down in this direction on this curve, right? So here is the curve, right? So I would expect to move it down like this if I increase it, right? And this is what is happening. It becomes a little bit more clear if we work with 1 component. So it says 1.5 picofarad, and we just move down on this line exactly as this one, this slide shows it, right? Parallel C, we move down on these lines in this direction. This is exactly what happens. So if I increase this, it will move down on this curve in the simulation. So what happens in practice? So I didn't have 1.5, I had 1.8 picofarad. And I just want to see what happens, right? So I prepared a little bit. Maybe let's go to the desk view. Okay. So this antenna here that we just measured, it has just 0 ohm resistors in this matching circuit. So there's no shunts and no, yeah, shunts are unpopulated, and the 0 ohm resistors are basically, yeah, just theoretically perfect 0 ohm, wouldn't do much to the transmission line. So, and now I have prepared some boards. I have to find the right one. This one not. So I have this one here, and try to make it such that you can see it hopefully better. So there is 0 ohm resistor, so the antenna 0 ohm, and then the shunt capacitor 1.8 picofarad, and then just 2 0 ohm resistors. So on this PCB we have 5 components for the matching circuit, and I can attach this, right? And then let's try to open VNAQT, right? And you can see that indeed we have the dip going down further. So it goes down to minus 16-ish dB, and the frequency shifted a little bit up. The point is now here. It is a different board, but this is how reality also is. You have a board on your table for development, or 10, to make measurements, and if you go into production and all the boards are like individuals, so there are some variants, of course, but this could be really matching well. So this is basically antenna, 0 ohm resistor, then the shunt, and then 2 0 ohm resistors. So, and this is why I will call it like this, 1P8F underscore 1, because it's at position 1. So, and then if we look at detune, I can actually load the data. So this is what we expected, right? So this is what we measured. The brown curve is what we expect, and the blue curve is what we got. So the theory is working somehow. So now it is working. We should do probably a different matching circuit, because it's not ideal, right? We are just moving this point on this one line. We saw already we can get more with more components, but yeah, we have to cover this in the academy. We will cover this. The academy, I will tell later a little bit more about it. So this is another board. Now I made an experiment, a small one. I don't know how well you can see that, but I have another board, and since we have five component matching circuit, we have 2 potential positions for the shunt. So in this variant, you have antenna, then a 0 0 ohm, a 0 0 ohm, then the shunt, 0 0 ohm, and then the UFL. So, and we will see what will happen there. So let me open up this, export the data, right? And also have to look on the watch, because we want to answer questions also. So if you have questions, just post them into the comments. I will look into that. So this dip goes a little bit deeper, and I think the point moved a little, but let's export that data. this is on position 2 from the antenna. And if we, I think I have to go out and in, right? And I will add this one, compare, rip. And as you can see, it is not the same, right? And this is an, I think, important lesson that you can see here. The matching circuit itself that I have in the PCB, it has a transmission line, and it also has components that are not ideal. And Attune doesn't know anything of this. So either you make your measurement and you model your antenna plus your matching network, and then calculate on which position you do what, then it would make probably no difference, right? You would get like the right thing. So I would have to model in this circuit here my other components and the transmission line and so on. And then it would give you other values. But you can also make some tricks where you basically move the reference point of your calibration. It's called like port extension. If you work with magic VNA, if you work with nano VNA, I think they call it electrical delay, right? And it's important how your matching circuit is designed and how you measure that. It's often a little bit trial and error involved. And yeah, why does the transmission line play a role? Yeah, the transmission line plays a role because it will basically move your Smith chart, right? So it will rotate everything. If the wave travels along transmission line, then you see the wave at a different angle, basically. Yeah. So this is we have some shift. So it's rotating around basically a curve in this 50 ohm, and then it also affects your matching. So, but this is also part, how to deal with that more in detail is part of another session. So now I want to say something about the Academy. I think I have said this already in the last session. We are working on getting up a course, an affordable course, which is very practical, where basically, yeah, which is intended for embedded developers. So people who work with wireless devices, engineers, and often they are not experts in RF, right? But they always need to work with this. And every wireless product has an antenna. We have designed many boards with antennas, right? So I don't know if this is working. Like this has antennas, right? You can see antennas on this device, or here's a device that has two antennas. So they're always there, and it's really helpful if you know the absolute antenna fundamentals. Okay, I just hear that we don't have questions yet. That's maybe a good thing. I don't know. Yeah, you can learn how to work properly with the VNA, what it is, how do you calibrate it, different methods, basically how to calibrate it, because you not always have a UFL connector in your design. Sometimes you have to calibrate open cables. Maybe you don't have a calibration kit, but you have a matching circuit. You can use that also to calibrate your VNA pretty well. Yeah, we'll make real antenna measurements and experiments. There are exercises basically, so that you can understand on a very practical level how you work with these antennas. And I hope this will help you with your career, with the results that you get, and maybe also answer many questions that are there around antennas. Yeah, I get regularly messages also on LinkedIn where I either see somebody copied designs of PCB antennas, and yeah, that's not always the best way to do it, right? You need to have the understanding what is happening there, because copying an antenna from one design to another um, will produce most probably bad results. You cannot expect that they work in the same way just by copying it, right? If you have the PCB as a different shape, you have a battery on the board, it all affects that. And yeah, this course is intended for people who do not have a lot of experience with that, but they need it. So, and yeah, in this session, we'll use the kit. So we are now planning basically this workshop, which goes over 4 weeks, one session per week. So you have also time to exercise and yeah, ask questions. So it will be 2 hours per session, which is, yeah, I think doable per week. And then you have 1 week to do exercises, measurements to gather data. We are currently setting everything up. It's planned to be started in, I think, September, so 1 month. We want to start with the first class. We have to see how many people sign up for this. People who signed up using this form, so behind this URL is a form where you can register your interest. If you register your interest, you will get more information about the first class, when it starts and so on, and how everything will be organized. Yeah, the antenna kit is involved in this, so it's good to have it once it's live in Elecrow. We can then you can purchase it there. It will be delivered in a short time. It's currently in production, and then you can you also get a voucher basically, so which you can apply then for this workshop, so that the learning material is cheaper basically. Yeah, we want to try to keep it close to this number with what you need. So questions. Now I need to, you can see now one questions. Do you also have to tune ceramic antennas that you buy off the shelf? Yes, you also have to do that. Let me see if I have a board here with ceramic antenna. No, this one has an PCB antenna, but if you are familiar with, probably it's hard to see for you, but I have here, let me try to make it bigger, like this maybe. You see this is a Nordic development kit for the NRF 9151, and it has an antenna by Kyocera. Yeah, and you can see here it's hard to get my finger there. You also have connectors to make measurements, and you also have matching components actually on the board, because yeah, the whole board itself usually is the antenna, and it affects the impedance and everything, how the antenna reacts, and you need to have matching there as well. It doesn't matter whether it's a PCB antenna or off-the-shelf ceramic antenna. Ceramic antennas can be helpful. You basically buy like, yeah, like an antenna design on ceramic substrate, but it's like copying an antenna from one PCB, like a PCB antenna from one design to another. It will change. It will not behave the same. It's the same with ceramic antennas. Ceramic antennas, of course, they have a small form factors, but yeah, but and they have complex structures, so you can maybe have a lot of frequencies, or they are switchable, for example. So they have tuning elements that you can attach to it, so you can make it work on many frequencies with a small PCB. Yeah, with a small PCB. The smaller PCB, the ground plane, the smaller is the bandwidth of the antenna. And if you are, for example, designing cellular devices, then of course you have to um, work with many frequencies in the lower bands and in the higher bands. And if your PCB is very small, that means you need to even make these switchable. So some ceramic antennas also have pins basically to connect capacitors using like switches, RF switches. Um, so the device can then, depending on the frequency it operates, choose the right tuning capacitor. Actually, this antenna, this SIFA antenna, you can see this here. Do I have it bigger? I have it not really bigger, but you can see it here. It has below the radiator here. I exposed some copper. That's ground, and the idea behind that is exactly to fit a tuning capacitor, so you can change the capacitance. Yeah, and you can do this also with switchable capacitors. So depending on the frequency you want to operate without changing the design and everything, you switch basically the tuning capacitor using an RF switch. Yeah, but they need to be tuned as well. Yeah. Why is antenna matching checked and updated on every PCB revision? Yeah, several factors like PCB revision. If you change the physical parameters of your PCB, so the thickness, the substrate, the dielectric, maybe the size, and so on. As I said, then you have to verify the matching again. Different materials can be used. You can have like, of course, solder mask that can differ. You can have different dielectrics, like FR4 is not a very stable dielectric, and you should ideally do your matching or your antenna design in a way that it can deal with these tolerances that you have. So yeah, this is why it's a good um, manner or a good approach to check your antennas basically. Okay, there's now a long question coming, I guess. Or not. So, yeah, it's actually okay. Yeah, wonderful. We just make it bigger, Sakshi. Ah, yeah. There's one problem which you could give some insights. Having water as a medium, RF does not work. Hence, sonar is used for data communication, but data transfer is relatively slow for long distance communication. Is there any way this data communication could be made faster? Yeah, waves. No, it's all waves. Light is also just a wave. So I'm not a sonar expert. I just know, yeah, you have a different medium. So our antennas here, yeah, we just work with air. Usually they are in air, no, so sometimes they are put in, of course, or close to water, like when you have something on the body, right? It's close to a lot of water. Yeah, different materials basically, or in different materials, radio waves propagate in a different way. Sonar waves, I'm not an expert on this, but I think it's much different frequency and so on. So you can use it in water, yeah, you can hear things in water, of course, but yeah, it is slow because I think you have relatively slow frequencies, and um, the frequency also determines basically the speed for the data communication. It's one important factor. Now, if you work with sonar waves, I believe I don't know any way how you can make it faster. But it's an interesting question. I will think more about it. Maybe I can answer later in your comment. So I will ask actually if we have more questions because I can't see it. Can I see it? I think also there might be a lag. No, I don't see any more questions. So thank you very much for your attention. I hope that you got something out of this session. We performed not a complete matching, but because I didn't have all the components here, I prepared it very short term, but I hope you got the idea of it. If you want to learn more about the PCB antenna, then check out PCB antenna design. Then maybe you check out our course that we will offer. And if you have any questions, any feedback, any wishes, like other things you would like to see in the IoT kitchen, other topics to be, I need a big amplifier for it. Yeah, then yeah, let us know. We also have this email, iot-kitchen@embever.com. You can send anything there. You can send questions there. You can send designs there. You can suggestions. You can send feedback, whether positive or negative. We appreciate it. So thank you for your attention, and I wish you all a very nice week ahead. I hope you liked it. See you soon, hopefully. Bye-bye.